In this video we'll run through the electrophilic addition mechanism, this time with HBr as the electrophile. Could be HCl. This first example shows ethene reacting with hydrogen bromide. In many senses hydrogen bromide is a more obvious electrophile than the bromine that we started off with, since HBr is a polar molecule, then the Br is permanently delta negative and the hydrogen is always electron deficient and so is more obvious in terms of being attracted by the carbon-carbon double bond. So our mechanism will look just like in the previous example. So the carbon-carbon double bond breaks, forming a bond with the hydrogen bromine bond breaks, the electrons go into the bromine. So note, we've broken the carbon-carbon double bond, we've formed a bond between one of the carbons and the hydrogen. The bromine has gained those electrons and is now negative. The right hand carbon lost its electron and is now positively charged. This species is the carbocation intermediate, so not very stable, and we'd complete our mechanism by showing the electrons from the bromine forming a bond between the carbon and the bromine, and there's our product from this reaction, bromoethane. Let's consider the mechanism now between propene and hydrogen chloride. So our mechanism would start in the same way, so the double bond breaks between the two carbons, and then the bond between the hydrogen and the chlorine will also break. And this is where we need to be a little bit more careful. So when the bond between the two carbons broke, this hydrogen can either be bonded to this carbon or to this carbon. Remember, this bond between the hydrogen and the chlorine is breaking to make a chloride ion. So if the hydrogen joins onto the left hand carbon, that will leave this central carbon positively charged, and this chloride ion will then join onto it, which will be different compared to if the hydrogen joined on to the middle carbon, leaving this carbon positively charged and the chloride will be on the end. So back to our mechanism, there are two possible options here. So let's go down the left hand route to start with. I'll add my hydrogen onto the end carbon, which means the central carbon is positively charged. Or I could add my hydrogen to the central carbon, rendering this carbon positively charged, and then my chloride ion will add onto there. Hopefully you can see this will lead to two different products. On the left hand side we've made 2 chloropropane, and on the right hand side 1 chloropropane. So the next question to ask is, will we make both of those products? Will we make equal quantities of those products? And the answer is no, we won't. And it's not to do with the stability of the products. So the preferred route comes down to the stability of the, please stay, of the carbocation intermediate that we had to go through. Let's just take a look at the types of carbocation intermediate that we might have. There are 3 types to consider. And what we need to look for are the number of R groups attached to the positively charged carbon. So, a primary carbocation. This will be attached to 1 R group. The other atoms being hydrogens. For it to be a secondary carbocation, that positively charged carbon will be attached to 2 R groups and 1 hydrogen, and in the case of a tertiary carbocation, you guessed it, there are 3 R groups attached. So why do these R groups make a difference? Well, the R groups contain a certain number of carbons, and these carbon groups will contain more electron density, certainly than the hydrogens which might be attached. The carbons don't like being positively charged, so these R groups being able to direct electron density towards the carbon will stabilise it, which means that tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations. So given the choice, we would go through a tertiary carbocation over a secondary carbocation over a primary carbocation. Let's go back to our reaction from before. So we said the important stage is to look at the carbocations, which I've highlighted here. So let's look at the carbocation on the left hand side. Here's the positively charged carbon, and hopefully we can see this is attached to 2 R groups and just 1 hydrogen, which makes this a secondary carbocation. Looking at the right hand root, the positively charged carbon is bonded to just 1 R group and 2 hydrogens, so this is a primary carbocation. So the secondary carbocation is more stable, and as a result we would make far more 2-chloropropane in this reaction than 1-chloropropane. So it's the carbocation that we are going through.